What about write string, right? So this is the first operand, 7 in this case. And 17 would be the second operand. So let's look at this. What's supposed to happen? So if you want to execute write string 39, and in data memory, we have this string stored in locations 3 through 9, then the string will be written out. So if you execute it, then the cat is written to the screen. Now, as I mentioned earlier, tj.data A represents the data memory location whose address is A. All right. So all you have to do is to write out tj.data first operand through tj.data second operand. Right. You have to, in this particular example, you have to write out all of this. Okay. So you have to write out all those characters. But you have to be a little bit careful, because if you look at tj.java, you will see that the array data declared on line 26 is an int array, right? It says int here. So therefore, if you just try and print out these array elements, you will get the integer values, not the characters. So please don't forget to perform a char cast on each value before you print out. Right? So you need a loop, you need a for loop to print out those values, but you've got to do a char cast. All right, so that's for more instructions covered. All right, so now instructions that deal with pointers to data memory locations. Now the issue here is, how does the virtual machine represent pointers? So so if you have pointer to, let's say, 11,000, right? One way would be to represent this using the number 11,000. And you could, in fact, do that, but that would make the job of the garbage collector harder. The purpose of the garbage collector is to free blocks of heap memory that are no longer accessible to the program. So the simple example of how you can have heap memory that's no longer accessible to the program, suppose I have a equals new int 1000, right? So this is the heap. And let's suppose that this is already allocated. So this will create an array on the heap, right? So I explained last time that there's actually a pointer that does this, but this will be an array of size 1000. And so in A's location, the effect of this will be to cause A to heap. So this is A sub 0, right? And this is the 1000th element of the array, A sub 999. But suppose immediately after this, you now write A equals null, right? So immediately after executing this, you execute. This would be a rather stupid thing to do, but let's suppose you did that. Then this would now be go away because of this, and now in here you would have the null pointer actually represented by 0. But now what's happened? You see, now we have this this block of heap memory that's just been allocated that nothing is pointing to, and the job of the garbage collector is in fact to free blocks of heap memory that have been allocated, but which are no longer accessible to the program, right? Because the point is that this is like a hotel room that's been given to the guest, and then the guest has left and thrown away the key, and now nobody has a key to that room. So the garbage collector looks for such rooms, and so basically it has to find all the rooms that are still accessible. So it's like looking at all the people that might possibly stay at the hotel and ask them to present their keys. And somebody presents their key, their front desk checks which room that key is for, and so if a certain key is for a certain room, then that room is still in use, right? But if there's a room such that nobody has the key to that room, right, then that room is not in use and can now be freed. All right, so if A equals null, that means the key to that block of memory has been thrown away, so the garbage collector can now free that block of memory. But this requires the garbage collector to be able to distinguish integers from pointers, right? So if this address is, let's say this address, so if so this address is 11,000, shall we say? So we have pointer to 11,000. Then if so this is the location of a variable, shall we say A. Then when the garbage collector finds this pointer, it knows this block of memory is in use, right? Here's the pointer to here. So no, but if A doesn't contain pointer to 11,000, if A just contains the integer 11,000, then that's not saying that this block is in use, because the integer 11,000 is not a pointer. So the garbage collector needs to be able to distinguish pointer to 11,000 from the integer 11,000. So that's why we need, so the question is how do we represent pointers? And if you use 11,000 to represent pointer to 11,000, the garbage collector would have to work harder to determine which locations contain pointers. So that's not the solution that's used. The more simple-minded solution is used in the TinyJ virtual machine. The solution that's used is pointer to A is represented as shown on page 4. All right, so let's go to page 4. Use of code interpreter.pointer tag. This is page 4 of the same document. So pointer to memory address A is represented by A plus pointer tag. What is pointer tag? Pointer tag is this number in hexadecimal, which in binary is this. So in other words, pointer to 0, pointer to address 0 is represented by this. Pointer to address 1 would be represented by this thing with a 1 at the end. Pointer to 2 would have a 1 here and a 0 here. Pointer to 3 would have 1s in the last 2 bits. So this is what you need to remember. Pointer to A represented by A plus pointer tag. Okay. And if you have a pointer, if P is a pointer, then P minus pointer tag is the address that the pointer points to, right? To convert from pointer to address, you subtract pointer tag. To convert from address to pointer, you add pointer tag. So now let's look at how we execute push data add 7. Okay, so let's look at what push data add is supposed to do. Here's push data add 17. All right, so you want to push 17 onto the stack, right? So you want to do this, right? So how is this represented? This is 17 plus pointer tag. So if we look at execution examples, push data add, right? Well, this is push data add 4, right? So you put on here 4 plus pointer tag, like that, right? So this is a pointer to the location of address 4. So this is would be 2 locations below tj.data2. All right, so that's push data add 7. 7 is the operand. It should push 7 plus pointer tag. In other words, push a pointer to the data memory location whose address is 7. So put 7 plus pointer tag into extrastack ESP, and then increment the ESP. All right, push local address. Now, what is that supposed to do? Well, push local address is supposed to push a pointer to the location with offset given by the operand in the currently executing method activation's step frame. So let's here. So push local address, right? So let's suppose this is the step frame of the currently executing method activation. So this is part of data memory. So again, somewhere in here. And so push lock add 3 is supposed to push a pointer to the location at offset 3, the 3 location here, onto the stack. Right? So it's supposed to push this pointer. But this whole stack frame is somewhere in data memory. So that's why I got 2 arrows. All right, so that's what push lock add is supposed to do. Now, one thing that you need to know now is to recall from page 1 that the FP register stores a pointer to the data memory location at offset 0 in the currently executing method activation stack frame. So FP plus K is a pointer to the location at offset K in that stack frame. So it's very important before you do the assignment to read page 1. All right, so before you work on these assignments, read page 1. So I've sometimes in past years had students send me emails that they couldn't do something with this assignment. And in many cases, it was because the students hadn't read page 1. So be sure to read page 1. So this is page 1. So the comment about FP is here. FP is a pointer to the data memory location at offset 0 in the currently executing method activation's stack frame. FP plus K is a pointer for the location at offset K in that stack frame. Right. So execution examples, push local add. So push local add 3, right? FP points to offset 0 in the currently executing method activation's stack frame, right? The stack frame of the method whose code is currently being executed. So push local address 3 must push a pointer to this location, right? Where the 3 is, right? This location here. So push FP plus 3, right? Like that. That's all you have to do, all right? So before, after. Before, after. Right? Just push FP plus 3. So push local address 7, similarly, should push FP plus 7. Right? So put FP plus 7 into ExpraStack ESP, and then post increment ESP. Okay, load from address. All right, so what is load from address supposed to do? Load from address dereferences a pointer. So if on top of the stack, you have a pointer to a memory location, load from address will replace the pointer with whatever is stored in that location. All right, so this is pointer to address 25. So load from address, when you execute it, will replace this pointer with 76,314. Right, so let's see this. So before, after. Again, before, after. So let's take a look at the description. If P is the pointer on top of the stack, right? P is in ExpraStack ESP -1, then execution of load from address should copy the value in the data memory location P points to, right? In other words, copy the value in tj.data P- pointer tag. Should copy it into that same location. Copy it into ExpraStack ESP -1. So copy that value into ExpraStack ESP -1. Load from address. So we've got a pointer to 23 here. All right, so it's pointing to address 23 in data memory. Right? So we need to overwrite this pointer with this value. Right? So before, load from address. Before, after. See that again? Before executing load from address, we have this situation. Afterwards, we have this situation. Okay. Now, data memory isn't changed, right? 7512 stays in data memory. It's just that this number is copied onto the top of the stack. ESP doesn't change either. All right. Save to address. Now, save to address pops a value and a pointer, and it saves the value into the location that the pointer points to. Save to address. So suppose you have this value on top of the stack, and you have this pointer underneath that value. So save to address will pop off the value and pop off the pointer and save the value into the location the pointer points to. So before, after. See that again? Before, after. All right. So save to address. All right. So suppose you have this on top of the stack, and you have this pointer underneath, right? ESP is 7. So 9855 in ExpraStack 6 is on top of the stack. So we pop off these two things. We pop off the number, pop off the pointer, and save 9855 into tj.data 23, right? Because this is pointing to address 23. So we end up with this, right? tj.data 23 and 9855. Before, right? And notice that ESP is 7. After, now ESP is only 5. Right? 9855 is the one here. So V is on top of the stack, and P is the pointer underneath V. then save to address should store v into the location p points to. In other words, it should store v into tj.data p minus pointer tag. And it should also decrease ESP by 2 to pop v and p off ExpraStack. All right, so that's 4 more instructions. Now let's look at instructions associated with calls of static methods and return from called methods. So we're going to need some shorthand. So spushY, well, first of all, page 1 tells you that ASP stores a pointer to the first unused location in the stack dynamically allocated part of data memory. ASP points to the first location above the currently allocated locations in that part of data memory. Right. So this is the stack dynamically allocated part of data memory, and ASP points to the first location that hasn't been allocated yet. Let's give an example. Okay. So initially, when there are no stack frames, ASP will point to here, the first location in the stack dynamically allocated part of data memory. After main is called, main stack frame is allocated, so ASP will now point to here, where my arrow is. Now, after main calls F, F stack frame is pushed onto the stack, so now ASP will point to here. Now, when F calls G, then G stack frame is pushed on, and so ASP will now point to here. When G calls H, ASP will now point to here. When H calls F, ASP will point to here. When F returns control to H, ASP will go back to pointing to here. Now, as H calls F, F returns control to H, right? So ASP will point to here. Right? H returns control to G, ASP goes back to pointing to here. G calls F, ASP goes back to pointing to here. All right. So spush is going to push a value y into the stack dynamically allocated part of data memory. And in Java, you would write it like this. And spopY will pop a value from the stack dynamically allocated part of data memory and store it into the location y. In Java, you can write it like this. So let's take a look at some pictures. So spushY, right? So you want to put y into here. So this is the stack dynamically allocated part of data memory. The gray part is already allocated, and the white part is unallocated. So ASP points to the first unallocated location. And so tj.data ASP minus pointer tag is here. So first, we have to do tj.data ASP minus pointer tag equals y. Okay, that's an spushY. So you put y here. All right, so now we've just done that. And now we increment ASP, right? So now we have this. So let's see that again in one step. So to spushY, we do this, like that, okay? Before, after. Okay. Now you could put the ASP++ here. We get rid of the ASP and just substitute ASP++ or ASP. And in fact, that's what I did. Right? If you have a look here, I put the ASP++ here. So the meaning is the same. So you can write it like that if you like. spopY does the opposite. It pops a value from the stack dynamically allocated part of data memory and stores it into the location y. All right? So in this case, W is put into y and ASP is decremented. So first, we can decrement the ASP like that. And secondly, we store the W, right, tj.data ASP minus pointer tag into y, like that. Right. So let's see that again. So before spopY, let's suppose we have this situation. Then afterwards, we have this, right? Before, after. And again, the minus ASP can be, we delete this and replace this ASP with minus ASP. Right? The meaning will be unchanged. Right? So spopY means this. And pass_param should spush a value that is popped off ExpraStack. So this is a value that's popped off ExpraStack, and you just spush that. Now, to understand the remaining instructions, we're going to look at a concrete example. So we're going to look at this example. Suppose that a certain method F calls a method G, like this, For example, let's suppose G is called in this print statement, right? But we're really interested in the call. And we're going to make a few assumptions in this example. We're going to assume that in G, 7 step frame locations are allocated for local variables declared in G's body. We're going to assume that the code memory address of the first instruction generated for G is 671. So the first instruction for G is 671, init step frame 7. Okay? That's a combination. So if you combine 1 and 2, that's the deduction that you can make. Also assume method G returns control to its caller using 713 return 4. Now you knew it was going to be return 4 because there are 4 parameters. But the assumption here is that the address is 713. And finally, suppose the code memory address of the first virtual machine instruction generated for this call is 44. So the instructions for this call are part of the instructions for F, and we assume that 44 is the address of the first instruction generated for this call. Okay? So the previous instructions in F are for something else, right? Not for this call. And now we will see how this call is executed and how the return will be executed. So this, by now you should be able to do hand translation, so you should be able to verify that this call gets translated into this. Now, I'm assuming that we have a call like this where we actually want the value, okay? So we don't want to discard the value because we want to print it out. So that's why there's no discard value here. So anyway, so by now, I remember on Monday, on the exam, you'll get a 10-point question or 1 or more questions worth a total of 10 points that test your ability to hand translate. So one thing you should be able to do is to hand translate a call like this into instructions like this. But let's walk through this code, see what happens. Right? Push num 17, all right? So that pushes 17. Pass param. So it pops off 17 and S pushes it, right? Pass param. Push num 23, pass param. So push num 23, all right? See, pass param. All right, so 23 now here. Push num 7, pass param. Right, so 7 has been passed. Push num 3, pass param. So we pass this into the step frame G. So now we're done with the parameter passing. Now it's time to transfer control to G's code. But there's an issue here, you see. We can't just put, you might think, why not just put 671 in the program counter? If you do that, then the next instruction to be fetched will be this in its step frame. So you would have transferred control. But that would cause a problem later on, because eventually when you want to return, you want the next instruction to be executed to be 53, right? That's how return works. So if you call a method, then when you return to the next instruction after the call. So you can't just overwrite the 52 with 671, right? That would be that would be wrong, right? Actually, it would be 53 because once you fetch this would say 53. But anyway, you can't just overwrite it. You have to save this 53 somewhere. And where is it saved? The answer is it's saved in offset -1. All right, so at this point, you have to look back at a page that I briefly showed you earlier. All right. In each step frame, other than main step frame, the return address is stored at offset -1. Okay. And the return address is the code memory address of the next instruction to be executed after control returns to the caller. So we need to, so once we fetch this, then PC contains 53. Now we need to put the 53 here. So we need to S push PC, and then we can set PC to 671. So let's watch this. So the first step is to S push the return address 53. Right? So S push PC. All right. So after S push PC, we have the 53 here. And now we have saved the PC in offset -1. We can then overwrite the PC with the 671. Like that. Right now we have 671. So now we're ready to execute the init step frame. Now to execute the init step frame, we need to change the FP so it points to offset 0 in the callee's frame. But we can't just change FP to this because when we return, we want to make FP pointer here again. So we need to save this pointer before we change the pointer to pointer here. And that's why we need to store this pointer in here. We're going to save this pointer in here. And now going back to this slide, the dynamic link is stored at offset 0. The dynamic link is a pointer to the data memory location at offset 0 in the step frame of the caller. In other words, it's a copy of the caller's FP. Okay. So this pointer needs to be put here. So this pointer will be the dynamic link. So the first step then is to S push the FP to save the call as FP in offset 0. Now we can actually set FP to point at offset 0 in the new frame. And finally, we can allocate space for the local variables of the called method G. Okay, let's watch this. So first we S push FP. So we put the FP here, right? So S push FP, right? So we do that. So this pointer has been saved here. Now we set FP to point to offset 0 in the callees frame, like this. Right? So that's step 2, right? Set FP to ASP minus 1. And finally, we increase ASP by 7, like that. And so now we have allocated the stack frame for G. Right? So let's see that again. We S push FP, we set FP, and we increment ASP. All right. So that is how we allocate the stack frame for the call. Now, how do we return? Well, we have to reverse this process. We have to pop off this stack frame. We have to make FP point to here again, and we have to make ASP point to where it pointed before. And we have to set the program counter to 53. Okay. So first, we deallocate the space used by the callees variables. Set FP, ASP to FP plus 1. Right? Then we pop the FP, S pop it. We S pop the PC, and we decrease ASP by 4. Let's look at a picture. So first, we deallocate the space used for the local variables. Okay. So we do this, right? So that was set ASP to FP plus 1. All right, let's watch that again. I'm sorry. So first step is to do this. All right. The next step is to S pop the FP. Pop this pointer back into here, which is what I just done. Let's see that again. We S pop FP. Like that. Right? See it one more time. Right? We put this pointer into here. All right. Now we S pop the PC. So the 53 has to be S popped into here. So watch this. It's going to become 53. Right? Like that. And finally, we have to deallocate the formal parameter locations. Like that. So now we're back to the stack frame of F being on top of the stack. Okay. So that's call and return. So I'm now finished talking about assignment 3. And it's not a bad time to stop, actually. So what you need to do before the final exam is to do the reading, right? So you're more fortunate than the students in the other 2 classes. They have their final exam on Wednesday of next week, right? But you have 5 more days. So be sure to do this reading and do this exercise. And remember, I mentioned that I will post these slides that show you, that walk you through the solution to this problem here. Okay. Exam 2 is this coming Monday, but of course, exam 2 is not cumulative. So nothing I said today is, all this stuff about assignment 3, that's not relevant to Monday's exam, right? But what I'm saying is in the other sections, the other 2 sections, they have their final exam on Wednesday, right? So what's happening with them is after exam 2, they only have 2 days before the final exam. So but you're luckier because you've got, after Monday's exam, you've got a whole week, right, before the final exam. So you're actually, you have much more time to do this reading than the people in the other 2 sections. But anyway, that's life. I didn't schedule the final. I would have preferred everybody's final exams to be on the day of your final exam. Then everyone would have plenty of time to do this reading. But the college decided that their final. Well, I mean, they have to make sure there are no exam conflicts. So so they're doing the best they can. So but anyway, so you guys are luckier than the students in my other 2 sections. All right. So are there any questions at this time? Yes, this is true. I can actually probably give it back to you if you like. The only thing is that I didn't want people to get confused. Exam 1 is not nothing on exam 1 is going to be on exam 2, right? So when you're preparing for a Monday's exam, there is no use for you to look at the exam 1 questions. But there is a case for maybe after exam exam 1, I will make after Monday's exam, I will make the exam 1 available again, so people can take a look at their exam 1 to study for the final, right? Maybe I'll do that. So between now and Monday, I suggest you study for exam 2, and if you have spare time, then do this reading. So you don't need to study lists and so on before Monday's exam. There won't be any list questions on Monday's exam. Okay, but so at some point before the final, I am going to make the exam 1s available to you again, so that you can take a look at those questions. But bear in mind that you're not going to get exactly the same questions. I mean, in fact, I try to avoid having questions on the final that are too similar to the questions on exam 1. I mean, I'm not saying there'll be zero overlap, but you shouldn't expect most of the questions you saw on exam 1, you're certainly not going to see on the final. Okay, so let me turn the recording off. Sometimes people have other questions, after I've done that. So, okay, so I've turned the recording off. Does anyone have any questions at this time? All right, so no one has. When did we get in my email? Let's see. All right, let's see. I sent you 2 emails about the exam, right? One about the question about the F grade replacement policy, and one. So there's this email, right? Question on exam 2 regarding the replacement policy. All right, so make sure you don't spend any time thinking about the answer to this. So I'm certainly not going to allow any time on the exam for people to work out the answer to this question. You're supposed to think this through, and when you see this question on exam 2, answer it straight away, right? In the first 10 seconds. Just enter whatever answer you thought of. But that's one thing. But the other thing is information re-exam 2. You're having trouble connecting to Venus. Well, I don't have control over Venus. Sui Wong is the person to ask for help with Venus. That's a departmental machine managed by the department and used by, Venus is not just used by this course, it's used by other instructors as well. And the department, in particular, Zui Wong, who actually manages Venus, should be able to advise you on any connection issues with Venus. But here's the information regarding next Monday's exam, so be sure to read this email carefully if you haven't done so already. Okay, so these are the exam 2. This is the point allocation on exam 2. Okay. Now, are there any other questions at this time? Okay, so if there are no questions at this time, then I will sign off. So I'll say good night, and I look forward to seeing you all on Monday for exam 2. So I'll see you in the Zoom room on Monday. So good night, everyone.